Thank you, Katya, for introduction. So I'll just proceed directly to my biography again. So my background is in plant physiology, biochemistry, and also in bioinformatics. That's how I finished PhD in remote sensing in 2021. And in the picture, you can see how I looked like before the PhD, and here how I look like after. So you still have time to reconsider if you're in doubt. I work as assistant professor at ITC and also in the research and development department of eLeaf company that does water modeling and plant productivity and evapotranspiration estimate. My talk is going to have 7 parts. So I'll explain why I decided to investigate this issue and what actually retrieval is and what the prior is, how RTMs retrieve, because I work with a scope model, and also, I mean, if you want to retrieve without a prior, you need RTM. Then what experiment was done, what the answer to the question, and then there will be a bonus part. I hope we're going to have time for that. So in practice, retrieval is the cornerstone of remote sensing because it's a translation of remote sensing data into information. Not so many people are interested in reflectance or in having an RGB image, but they're interested in information. For example, about leaf chlorophyll content, and maybe even more importantly about leaf nitrogen content, canopy nitrogen content. So this process of a translation of reflectance into meaningful quantiles is called retrieval. How well can we do that? Well, let's look how people did it previously. Leaf area index and leaf chlorophyll content are the two maybe main components. They affect spectra seriously, and they're expected to be retrieved quite well. And well, yeah, we can say so. For example, in this work, leaf area index was retrieved with around R² of 0.6, but leaf chlorophyll content, the main green pigment that makes plants green, is around 0.2, 0.3. It's a little strange, but okay, let's see. Maybe it just wasn't the topic of the study. Okay, then the next work, this was done on potato. In total, the performance of leaf chlorophyll content 0.3, of leaf area index 0.2. So we explained 20% of variability in the triad from remote sensing. Okay, let's look further. Okay, in this work, leaf area index is on the left and chlorophyll content on the right. And the authors advocated the multi-angular retrieval. So if you retrieve only from one angle, you receive 0.6 for LAI and again 0.3, some low values for leaf chlorophyll. If you use multi-angle, it's almost perfect. All right. And then the final literature review example that is not only about inversion of radiative transfer model that I'll explain later, but also PLSR, the statistical method. Again, leaf area index on top, chlorophyll in the bottom. This also investigated the influence of the flowering stage. So the all points are in gray and the blue points are in a proper phenological moment without flowering. So, but anyhow, LAI was retrieved either with 0.4 or was not retrieved because R² of 0. Well, chlorophyll 0.4 were also acceptable. So the motivation was that the accuracy of retrieval of basic plant parameters, leaf area index, leaf chlorophyll content, from ground hyperspectral reflectance varies from 0 to 1 in practice, and it's more often closer to 0. So how can that be? So what is the bottom line below which we should say maybe we do not accept these retrievals anymore because you don't use your data or you misuse your data? All right, there is one thing I explained already, that what retrieval is, and there was also term prior in the talk. So what prior is? Prior is, there will be 2 or 3 definitions of that. Or one is what we usually do with machine learning. We showed 70% of the data to the model, and it was able to predict the other 30% correctly, which, yeah, good. And it is useful indeed in cases. I think the pros is when we retrieve complex features that do not have spectral signatures. For example, leaf potassium content. It's not yet in the relative transfer model. And to my knowledge, in the reflectance of the leaf, we will not be able to see the signal. But if there is something that we're not able to see, but the machine learning can help us with, then we can use this kind of prior when we show part of the data and we use the rest. But what it leads to, the consequences, the limitations of this approach, the disadvantages, is that we then limit remote sensing to just upscaling on a single image. So instead of using the whole time series, the whole data available, we just use one image around the training area in the moment when we trained it, so in instantaneous moment, and then we produce one map that is valid for technically for 1 day that the campaign was held. This is still interesting technique, as I said, because there are parameters that need this retrieval. For example, my colleague from Natural also department, Mariana Pelju, they did retrieval with Prisma hyperspectral satellite for these nutrients. As you can see here, maybe you don't see it, but there are red dots in the fields. So this is where the field campaign was taken. And this is the performance of, for example, potassium retrieval, which changes day per day. I wasn't sure if they changed the algorithm, also retrain the algorithm day per day. But anyhow, this is what the prior can do for you. What could you do without a prior? Okay, how can a prior be used differently? Then we should take a look at my favorite review about retrieval that I cite everywhere where I talk about retrieval. There are essentially two ways: the regression-based and the relative transfer model-based. And these guys, the regression algorithms with all this big toolbox, they all need data. And this data is, I mean, in my terminology, we call it prior. So they are empirical methods. But those guys, they're physically based. They do not need data. So in practice, in my talk, I discard these old methods. But what I leave here is, of course, hybrid approach, because there's a trick when you replace the training data with RTM simulations. But essentially the same thing. So one more, the last fundamental step of understanding the relative transfer retrieval is what we do. And I recorded a little video that I'm going to launch in the next. But what we do essentially with relative transfer models and remote sensing, we try to fit the curve. Here, the curve is black is the one that we want to fit. I think the video starts now. Yes, and the blue is the one that we try to fit with. But how we fit? We minimize cost function, which is just a difference. In this case, I mean root mean square difference. In this case, so we can change this very simple example, two parameters, chlorophyll and leaf water content. When we change it, we see that the spectra changes, cost function changes. In this case, we see that we go in a wrong direction. The region of the spectra that is influenced is here, but we are going further and further from the target black curve. And this cost function tells us about that. It goes up. So what we can do, we can make steps in the proper direction. And finally, can be satisfied. Okay, we close this gap. Now we have to close the gap in shortwave infrared. And okay, we have as a parameter. Whoop, very, very nice step. We reduced the error a lot. We reduced it. Finally, the curves are almost perfectly fit. When there are two parameters and the reflectance is modeled, it's very easy and you can achieve the perfect optimization. But when we are in a real world situation, and for that, I can refer you to the talk already recorded in our cost webinars about Nmap box and it's a QGIS box. You can upload one curve and you can see many parameters. I mean, you cannot see them now, but there are leaf parameters, canopy parameters. You could try to fit the curve. It's very good exercise. It's a minute 13 of the video if you don't want to do it yourself. And you will see that there are many possible options to fit the same curve. And this is called ill-posedness. What I've just showed you is the technique that I'm going to discuss further is numerical optimization. So what we just did with toggles, the model does during inversion with the gradient descent algorithm. The algorithm is ill-posed when several parameter combinations can result in the same fitting of the curve, the same result. So, and the common mistakes connected with this technique is, first, when we use under-domain systems, and for example providing less bands than parameters. In this case, MATLAB algorithm, for example, even gives up. It says, I don't know how to fit 16 parameters, 16 unknowns with 12 knowns, for example, in case of Sentinel-2. And the second, quite common, is the retrieval in irrelevant spectral region. For example, we saw just now that chlorophyll, for example, reacts in has effect in the visible near infrared region. So we cannot retrieve chlorophyll in shortwave infrared region. There is no signal. The same goes backwards. That leaf water content retrieval from visible near infrared spectra, where many spectrometers are now, it's not possible with this technique. People always come to me with this question, but no, you cannot. Look at this. We know where each constitutes affects the spectra. If your sensor ends here, if you have only visible and near infrared sensor, you cannot retrieve water, at least not with radiation transfer model. There's no signal. I mean, it can give you value, but the value won't make any sense. All right. The final remark: how can we use prior? Well, in this case, we can extend the cost function that you already saw with the part that minimizes the difference. So we say to the model, okay, you can vary chlorophyll content from 0 to 100, but please stay close to the initial value. We know that we measured in the field in this area, the value should be 40. Okay, well, it's 40 plus minus this number, the standard deviation. Well, please stay close. This is, I think, the way to achieve peak performance, because that was showed in the work of Marco Celesti, because chlorophyll you retrieve with 0.94, LAI 0.97. Those are absolutely outstanding results. But again, whenever you use prior, you are limited to the day when you collected this information, when you measured this information. So what I try to answer in this work is, how bad can retrieval be without a prior? So for that, we went to the field, and I work in the Netherlands, so we went to potato field. We measured, we had many plots. We had two fields actually. Nitrogen was added to different plots to create variability in tribes, and we succeeded there. So what we measured was the ASD reflectance, of course. Well, we measured radiance and we computed reflectance. Then we measured leaf chlorophyll content with photosynthesis equivalent of SPAT, if you know, and leaf error index. So about ASD reflectance, one moment, we tried to minimize the error as much as possible. So we came up with this setup where ASD fiber is attached here, and the white panel is portable, so we compensate for the absence of cosine receptor of the ASD. So we took white reference, then we pulled the bar away, we took ground, and then we immediately pulled the bar back, and we took the white reflectance again. And at the end, at the moment of the white reference, the moment of measurement, we interpolated the white reference. Well, not this one, we interpolated in time, but anyhow, this was a way to minimize the influence of clouds that are not supposed to be there, of course, but they are always there. So we always corrected for white. So we recorded radiance, and the radiance and irradiance in this way. And the more steps that we did, we already debiased LAI, and we convert SPAT into actual leaf chlorophyll content, because none of those measurements, neither LAI 100 measures through LAI nor SPAT measures through chlorophyll, has to be corrected. And we retrieved soil parameters from bare soil spectrum. It was fixed for 1 day. This was the corrections. The measured LAI, the LAI that the instrument showed was always higher than the LAI that was truly measured, through LAI destructively measured. So we had to correct for that. And chlorophyll was also always higher than the truly measured in the lab chlorophyll. So we had to correct. Without that corrections, the RMSEs just get +1 here and +20 here. And the soil parameters, so essentially the scope model that we used is a ProSail with soil. So we used soil parameters there as well. And these are the results we came up with just for one plot, one variety. Leaf array index measured had this trend, retrieved had that trend. They matched quite well. The chlorophyll content was going down and was going down also based on reflectance, and it was also correlating with the true measurements. So the answer is how bad the retrieval without prior can be. The retrieval, I think at the bottom line, the retrieval can be 0.53 for LAI with this RMSE of around 20%, and the chlorophyll of 0.63 with again RMSE around 70%. And we did not succeed in retrieving any water or dry matter from this time series. Maybe also because no variation, no correlation. We were not able to create the variation in water content and dry matter, so we were not able to retrieve. So we were able to retrieve, but we retrieved the values that were basically point to point. So it's not proper. I think this is the main conclusion of the work. My main message. We did not use prior. We used only reflectance. We used it in many timestamps over the growing season. So it's a little surprising if you receive results, if you retrieve the radius transfer model and you retrieve worse results than this, especially when you use prior, it will be very surprising. Something might go wrong. So if you remember these numbers, 0.5, 0.6, if you receive lower correlation or higher RMSE, then probably there is still room for improvement, which could be quite simple. The bonus, I know that I exceeded already time by 2 minutes, but the bonus is still important. There is a smart prior that can be added to time series, which is the value of the previous day. This article was, why is it smart prior? It's a smart prior because you don't go to the field, you don't measure it in the field, you are independent on the field data. But you're still a little bit dependent on your knowledge of the dynamic of the parameter. So what is happening here? This article is published so that you can see the details. If you just retrieve with what I did now from satellite data, so it's already satellite data, there might be some imperfectness of atmospheric correction, or there's some other errors that lead to jumpy LAI, and it's not physically possible. The LAI cannot be 5 in one day, then 2 in the other day, then 5 back in the next day. So there's something wrong. If you do it, if you post-processing, you just smooth these values like Modis does, and this is okay. But if you want to do the processing near real time, then you probably have to say, okay, in the previous day, the value was 5. So I'm expecting the value from maybe 5.1, from 4.9 to 5.1, because LAI cannot increase over day. And that's what the page did. So this is smart prior. And you see that the curves resulted in quite smooth, but the difference is that it's not post-processing, it's near real-time processing. So when the new image comes, it's a Kalman filter. When the new image comes, the curve already, the retrieval already knows what was before, and it makes it quite smooth. All right, that was the end. Thank you.